All right. All right. We're still continuing with our complex analysis. Today, we want to look at complex series. Now, complex series basically have the same properties as real series. In the sense that if the function is analytic, you can actually express it in terms of a series which has powers. You can expand it about a given point. So we'll start with the definition of a Taylor series. So for a Taylor series, uh, if it is analytic within the interior of a circle C, which has a radius r, and the center of that circle being z naught, then for each point in the interior of that circle C, the function can be expressed as uh, f r. This is the rth derivative, z naught over r factorial multiplied by z naught. So this thing which is not the which is not the z minus z naught to the power r, which is common to all series expansion, is called the coefficient. So the coefficient can be obtained in terms of derivatives. So if you know the derivatives, you can get your series expansion. So it will converge anywhere inside that circle C. But if you expand it about the origin, the series becomes a Maclaurin series. The series becomes a Maclaurin series if you expand it about the origin. So, so that's basically the definition of the Taylor series. So let us go down and see how we can do this. So the evaluation of the evaluation of the terms of the series depends on you being able to differentiate that function the number of times that we have. So let us start with this one. We want to find the Taylor series for z is equals to 1 over root of 1 minus 2z about the origin. In other words, we are saying this is a Maclaurin series. We want to obtain, so you can expand it for any number of terms, but I think we've just decided to get the first 6 terms, which means we are going up to z to the power 5. So we're going to differentiate 5 times because it's the first coefficient we can obtain it by just substituting for z equals to 0 there. So we're going to differentiate and then substitute z equals to 0 into that. So the first derivative is given by that. It's 1 over 1 minus z to the power 3 over 2. The second one is minus 5 over 2. So what is happening in this case is that the series, the numerator of the series are just increasing by 2. In other words, we are just adding two halves, which is just 1 to every subsequent term. So with that, you can quickly get a pattern of what is happening here. And also, the other numbers, you can get a formula for this. You can get a formula for the number, the 1, the 3, the 5, the 15 in terms of factorials. So the numerators, if you now substitute z is equals to 0, what will happen is in the denominator, what you are going to have is 0. In fact, all denominators are going to evaluate to 1, which means if you evaluate it at 0, you just get the numerators, which are 1, 3, 5, 15, and 9, 45. So those are the numerators. And if we expand it, if we just write it, then we are going to have that series. We are going to have that series, the series for the function. So it is just basically this series 1 plus z plus 3 over 2z squared and so forth. Uh, we have gone as far up as 5 terms. So this is just an evaluation of a Taylor series by using a direct calculation of the coefficients in the terms. So sometimes to get our series, you might need to manipulate first your terms, or use some other geometric properties that we have. One that is crucial, one crucial geometric property that we have is that of the geometric series. So the geometric series is a simple series where you have increasing powers. So of whatever. So the first one, this is the power 0, raised to the power 1, raised to the power 2, and so forth. If you sum the geometric series to infinity, you get 1 over 1 minus r. So this is a geometric series where the common ratio is r and the initial term is r. We know the sum to infinity of a geometric ratio is a over 1 minus r. So it's just basically that. So the geometric series is a very simple series, and you will see it's important when you evaluate the next series, in particular the Laurent series. So I just want to remark that the Taylor series, they start from r equals to 0 to infinity. It has positive powers. It has positive powers about the point where we are expanding them. So we go to the next form of series. It's still a Taylor series. We still want to get a Taylor series. But now here's what we want to do. We want to find the series of z plus 1 over 2z plus 1 and multiplied by z plus 2. We want to find it above this above over this interval so that it converges in this interval. So what happens is this. Uh, this you want convergence in a circle of radius 1 because this is your z naught. It's about z naught, and then you want it to be a radius 1. So you want it outside that circle. So you have from the point 1, you draw a circle of radius 1. So it will go to 2, it will go to 2 on the other side, then to 0 on the other side, and go up to 2 in the other direction. So to plus 1 and minus 1 in the other direction. So it's a circle centered at the point 1. The point 1 on the Gantt diagram will be on the point 1 on the Gantt diagram. It will be on the real axis. So how do you do this kind of series? What you do is this: you decompose this into partial fractions. So decomposing this into partial fractions, this is a 2 there. You decompose this into partial fractions, then you are going to have what? 1 times 3 times 2z plus 1 plus 1 over 3. So that is the decomposition. Now, what we want is to have a function which is in terms of z minus 1. So what we are going to do is to rewrite this expression. So instead of 2z here, instead of just 2z here, we're going to have 2 times z minus 1. So if you make this adjustment, there will be a minus 2 here, but you need to get, there will be a minus 2 here, but there's also a minus 2. For you to get a plus 1, you need to add a 2 here. Then for the other one, if you readjust, and then you have a z minus 1 here. If you subtract 1, if you want to get 2, you have to add that 3. So we've adjusted this so that it is in terms of z minus 1 and z minus 1. So it's just a matter of shifting by 1. If you subtract a 1, you just add it to the other. So here we subtracted a 1, so we add a 1 to this 2 so that it becomes 3. Here we subtracted minus 2. We subtracted, there's there's a 2 there. You subtracted minus 2. So to readjust it, you just add. You don't add anything. You just to this, so that this 1, you just add a 1 there. The 1 that you subtracted here, you just add it to this 2. It becomes 2. So now our series is going to be this. So what we are realizing in this one is that 2 is going to be a common factor. So if you factor the 2 out here, it will go outside. So you'll be left with a 1 here. This one becomes a 1. This one becomes a z minus 1, because this 2 would have been factored out. This 2 would have been factored out. So this 2 has been factored out. And for the other one, there's a 3 and a 3. There's a 3 and you divide this by 3. So if you divide this one by 3, you are going to have a 3z minus 1, a 3 outside, so there will be a 9 outside. And then the other 3's are not there, because there's a 1, the 3 which comes from the 3 which is outside, and already this other one. So now what we want is to write this again in terms of for it to converge, for the geometric series to converge here. The modulus of this series and the modulus of alpha should be 1. So we want that as well. So what we have is, what we want is just modulus of it. What we want is z minus 1 to be greater than 1. So that condition is the same as 1 over z minus 1 less than 1, which is what we have here. So this is just the open bracket. So that if we have that condition, then we are okay. And we are ready to use the geometric series expansion for that. So now we write it in this form. We factor out the z minus 1. It goes outside with the 6. So it will be 1 minus 6. So if you multiply this out, this z minus 1, if you multiply it inside, it will give us the original expression. This one, you factor out this z minus 1 again. Now we have a 1 over z minus 1, which is basically what we want. And we take this one to be our alpha, and we take this one to be our alpha. In this case, it's a plus here, so it means it's negative, because you are going to have minus 1 and minus 1. So you are going to, this is going to be, the negative of this is going to be your alpha. In this case, the negative of this is going to be your alpha. So you can write this series straight away in terms of the summation sign, because this is your alpha for the first one. So what you have outside, then this alpha here, and plus here, and this alpha here. So if we just manipulate this, we take the 1 over 6 inside. The 1 minus 1 over r will remain there. I'm just, for the first one, I'm just taking the coefficient which does not have s, which does not have z. So it is going to be this, and 1 over. There will be an extra 1 z minus 1. That's why you have that plus there. It's the same thing here. Take the z minus 1 inside to introduce an extra z minus 1. Then you are going to take the minus 1 and the 1 over 3. There's a 3 outside as well. So there will be 2 of them. So there will be another t added to the 3, which is another 3 added to the 3 to the power r. So there's this 1, and then the 3 to the power r. They will give you this one. So now, because we are adding them from 0 to infinity, 0 to infinity, you can bring them under the same common, because our powers are common, are the same. You have 1 over z minus 1 to the power r. It's common. So you are using the same one. So you use that common one, and it will give you the same thing. So what you factor out now is the 1 minus r is common. What will remain here is 1 over r. And what will remain here is 1 over 3r. So the series expansion of this is given by this, and it is in the sigma form, is in the sigma formation. So that's the series expansion for this. So Taylor series with one, which we did a direct calculation. The second one, we used the geometric series to obtain the series expansion. So series, you can expand them using any other method. You can even use standard series. The series for cosine, we know them. The series for exponential function, the series for log. Those standard series still apply. Those standard series still apply to the case of complex valued function. Now, the second uh, the second type of series that we are going to do is the Laurent series. Now, uh, the Laurent series, the Taylor series, we expand it in a ring, either inside the circle or outside. But the Laurent series now is two. You expand it uh, in a washer, or you just consider two concentric circles. So you have two circles, C1 and C2. They have two radii, and they have the same center Z0. But the first one is a smaller radius, and the other one is a smaller radius. So you get something like a washer. You get something which is like a washer. So on the in the interior of the washer, you can actually get a series for every point in the interior of that washer. S. You can you can get a series expansion of positive and negative powers of Z. So your f of Z will be 1 r from 0 to infinity. So the first part are the positive powers, plus the second part of the series are the negative powers. So it is both positive and negative powers. And in our in the Taylor series, our our functions will our functions were expressing them in terms of derivatives. But here in the Cauchy integral theorem, if you look at the Cauchy integral theorem, this thing here is just also a derivative, which is similar to the power to the coefficients of which we had in the Taylor series. So the coefficients are just going to be for the positive part, you are going to have 1 over 2 pi I, the integral of this function. So this function is its center. The center of that circle is this. You expand it about points outside, inside that circle. So you do this for r from 0 to infinity. The other one now. So what is happening here in the denominator? The power is the r is positive. You have exactly the same thing for the negative powers. The r will be negative. So you can just if you can evaluate this integral, then you can obtain the power, the coefficients of that, and you have a series, a Laurent series expansion of that. So fortunately, you don't really need to use this all the time. You can actually calculate the series without resorting to this version of integrating the terms. I think I'll show you both cases in the short while. So here is what we want to do. Let us look at this example. In this example, we want to find the series for 4 over z, z minus 1, and z plus 3. That is valid for modulus of z greater than 1. So there we go. The first thing is to decompose the function into partial fractions. So if we want to decompose this, we make this a over the first one and a over this b plus b over the second one. It is equivalent to that series expansion, and it is going to give us both a and b being equal to 1. So the region of validity is 1 less than modulus of z. If you just rewrite it with the inequality facing the other way, these two inequalities are the same. So you always want a situation where you have it as less than 1. So if you divide both sides by z, you have 1 over z less than 1, which means there's modulus of 1 over z should be less than 1. So it is this 1 over z which we should use in our geometric series. And for the other one, if it's less than 3, for modulus of z less than 3, it means you can divide both sides by 3, and you have z over z times 1 over 3. That case is also valid, because if here is less than 3, then you have the other one is just less than 1 over 3. So you use this one for the first series and this one for the second series. So let us go back to our function. So in the first one, we're going to factor out z, so that we have 1 over z. In the second one, we're going to factor out 3, so that we have z over 3. So the geometric series is going to be this. In the first one, there's the 1 over z, here, which is outside. That's I'm keeping outside. So the series is for the terms, for the term in brackets. Our alpha in this case is 1 over z. So you have your 1 over z, 1 over z squared, and so forth up to infinity. We are going to subtract 1 over 3, which is outside. For the second one, our alpha is minus z over 3. That's what we have here. And I've written it up to for both cases up to the power 4. So you can actually add this. You can actually look at what we have here. So the first one is 1 over z, then 1 over z squared. So there are some terms for the first one. It will generate a whole number. The first series will generate a whole lot of numbers, a whole lot of terms, an infinite number of terms, which are negative. So these are the negative terms, negative power, which have negative powers. For the second one, starting with the minus 1 over, you have 1 over 3, the 1 over 3, but you have to subtract, there's another term there. So for the 1 over 3 and the other ones, you are going to have positive powers. So that, then there's the positive power, and they go on like that. You have your positive powers, and you have an infinite number of terms. So this series has both positive powers and negative powers, and they are all increasing. And they are all going to infinity. They are all going to infinity. So if you combine them, you have this last series as your Laurent series. Your Laurent series can have both positive and negative terms. It has both positive and negative terms. So now what we want to do is this. What we want to do is we want to find the series expansion of something similar to what we did earlier on. But this time, we want to use a direct calculation. The just ended example, we used the geometric series expansion. Now for this one, we want to use a direct calculation. So what we are saying is, we are going up here and calculate these terms. We are going to calculate these terms by just directly integrating them, not going via the the geometric series expansion or any other thing. So we check it here. So for the analytic part, the part that is analytic is the part which is the positive powers. We are going to have our AN. So it is going to be this. This is the expression for I haven't substituted anything here. Now, if I substitute f of z, which is 4 over whatever, it's 4 over, then it's 4 over z minus z over r. So we're going to use the Cauchy integral theorem. Uh, we are expanding it about the smaller one. This is the smaller circle. The inner circle, this inner circle is the one which is z minus 1 as the series, as the center. So you get that in the bottom. So the rest goes up in the numerator. This expression is the same. So if you have it that like that, we can actually use the Cauchy integral theorem. This is now equals to this is now equals to 4, that 4, and you just evaluate it at z equals to 1. This is your z naught. So you evaluate it when z is equals to 1. In the denominator here, you're going to have 1. And as the cz is going to be 1. So it's 1 plus 4. You are going to have 4, and this raised to the power, the 1 raised to any power is 1. So this simplifies to 1. So the positive terms, are all the positive coefficient, the coefficients for the positive terms are all going to be equals to 1. So we go to the what we call the principal part, the part where the derivatives the part where the coefficients are negative, the powers are negative. You get it this way. It is this. What is changing is that you now have a negative number there. You substitute for z like what you did before, you get this. Then, when you substitute for z, this is the second one. This is the outer. This is an annulus where the inner radius is 1, the outer one is 3. So you want this outer one now to be down there, and you put the rest in the numerator. So if you evaluate this, if you use the Cauchy integral theorem, it was going to be just evaluating this at the numerator of this, and you substitute z equals to minus 1. If you substitute that, you get this as just being minus z over 3, because you are going to have minus 3 here. So there's going to be you are going to just have, you substitute here, you are going to raise minus 3 to the power minus 1 times z. This, the 4 and 4 are going to cancel. So the minus 3 will go into the numerator. And there is a negative number arising from the division of minus 4 and 4, which is this. So this is the coefficient of the positive terms. So we now combine them. This is the coefficient here for the positive one is 1. So all the positive ones are going to have 1. And if you substitute r equals to 0 here, the first one will be as 1. Then the other one, you start at r equals to 1. And then you have the rest of the terms. You have the rest of the terms. Then you have the rest of the terms as z times z to the power r over r. So the negative powers are going to be there. So this is the series expansion, the Laurent series expansion for that last example, which we just did. So this is the issue with the Laurent series. So with the Laurent series and the Taylor series, two series expansion, one with positive terms only, and the other one with both positive and negative terms. So for the time being, now let us stop here. Then we'll move on to the next section.